Okay, let's just dive right into this explainer. We're going to look at something pretty wild today, how taking a simple piece of wire, wrapping it around a piece of iron, eventually evolved into an engine design that might literally take us to the stars. It's an absolutely incredible story of fundamental physics meeting brilliant engineering. I mean, we interact with electromagnets all day long, usually without even realizing it. But the exact same physical principles ringing your doorbell? The Department of Energy is actually studying them right now as a way to propel human-made objects deep into space. How cool is that?
Here's our roadmap for the journey. We'll start with the sheer power of temporary magnetism, then look at the early pioneers who cracked the code. We'll break down the anatomy of a solenoid, figure out how to design the perfect coil, scale things up from everyday doorbells to giant MRIs, and finally, look at electromagnetic space propulsion.
All right, Section 1, the power of temporary magnetism. Let's start with the basics. Think about that permanent magnet holding up a photo on your fridge right now. Its magnetic field is always on. It's just an inherent property of the hard materials it's made from. But an electromagnet, it has a completely different superpower. Its field is entirely temporary. Because it relies entirely on a continuous flow of electricity, you can turn it on and off whenever you want. And even better, if you tweak the amount of current flowing through it, you can perfectly adjust the strength of its pull. It is, essentially, programmable, on-demand magnetism.
Moving on to Section 2, the pioneers of the electromagnet. Now, this whole idea of controlling magnetism didn't just appear overnight. It was figured out during this incredibly busy, highly competitive decade in the 19th century. Literally, in just 10 years, we went from, hey, look at this weird observation, to heavy-lifting industrial power. In 1820, Hans Christian Ørsted noticed his compass needle twitching near a battery, and André-Marie Ampère actually formalized how currents create magnetic fields. Fast forward 1824, and British scientist William Sturgeon wrapped 18 turns of bare copper wire around some varnished iron, creating a tiny 7-ounce magnet that lifted 9 pounds. That was a massive deal. But the real game-changer hit in 1830. American scientist Joseph Henry realized that if he insulated the wire with silk, he could pack multiple layers tightly over each other without them shorting out. And that simple tweak, it allowed his electromagnet to lift a staggering 2,063 pounds.
Let's hit Section 3, Anatomy of a Solenoid.
So how do you actually build one of these things, what engineers typically call a solenoid? Well, honestly, the basic recipe hasn't really changed since Joseph Henry's day. You can literally test this physics at home. Grab a standard 6-inch iron nail, wrap it super tight in some 22-gauge insulated copper wire, just strip the very ends to make a connection, and hook those ends up to a basic D-cell battery. The absolute second you close that circuit, electricity flows, and boom, a magnetic field radiates outward. Wrap the coils tighter and you get a stronger field. But you might be wondering, why do we even need the iron nail in the middle?
Well, what happens inside that nail at the microscopic level is totally fascinating. Before the power is on, the atoms inside that ferromagnetic iron core are just chaotic. They're pointing everywhere, completely canceling each other out. But when that electric current surges through the wire, the magnetic field penetrates the iron and literally forces all those random atoms to snap into perfectly uniform magnetic domains. They all start pulling in the exact same direction together, which massively multiplies the field's strength. And the moment you cut the power, the atoms randomize again, and the nail instantly drops whatever it was holding.
Up next, Section 4, Designing the Perfect Coil.
Now, if you want to scale this up from a little D-cell battery to serious industrial power, it's not as simple as just throwing more wire at it. Engineers have to be incredibly strategic. You'd probably assume that to make a stronger magnet, you just wind a massive, super thick layer of copper wire around the core, right? But think about how that works in practice. Surprisingly, a thicker coil winding is actually less efficient. Here's why. As you add layers, the outer turns get physically wider. They have a longer circumference. That means they use more wire per turn, giving them double the electrical resistance, which creates double the heat. But because they're sitting much further away from the center axis, they only have half the magnetic influence on the core. So engineers are constantly walking a tightrope, balancing copper usage against actual magnetic efficiency.
And there's a huge catch here. Heat is basically the ultimate enemy of the electromagnet. This brings us to a crucial concept called the duty cycle. Let's say a designer needs a massive amount of pull force, but doesn't have a lot of space. They might push 4 times the normal power through a tiny coil. But if they do that, the duty cycle might drop to, say, 10%. That means to keep the wire insulation from melting and ruining the whole setup, the electromagnet can only be turned on for 10% of the time. It absolutely has to sit there, turned off, cooling down for the other 90%.
All right, Section 5, From Doorbells to MRIs. This perfectly optimized, on-demand magnetism is literally solving massive problems all around us, scaling from tiny microcomponents to the largest scientific machines on Earth. I mean, you benefit from this stuff constantly. When a guest pushes your doorbell, they're completing a circuit where an electromagnet magnetizes a clapper that hits a bell. Ding dong. In a wrecking yard, massive electromagnets easily pick up thousands of pounds of scrap metal and drop it just by cutting the current. Got a wireless charging pad? Yep, you're using oscillating electromagnetic fields. And in the high-stakes world of modern physics, gigantic particle accelerators rely on ultra-precise electromagnets to steer subatomic beams flying at nearly the speed of light.
But if we're talking medical marvels, the MRI machine relies on perhaps the most impressive commercial application out there: massive superconducting electromagnets. By cooling specialized coils down with liquid helium to near absolute zero, the wires hit a state of superconductivity. They carry electric current with virtually zero electrical resistance. None. This is what lets MRI machines crank out incredibly strong, continuous magnetic fields of up to 3 Tesla, all without bursting into flames from the heat standard copper coils would make.
But all that extreme, delicate cold brings a terrifying safety risk, known in the industry as a quench. If the system suddenly loses its superconductivity, maybe due to a tiny temperature fluctuation, all that massive electrical energy stored in the coils instantly turns into heat, and I mean instantly. This causes a sudden, violent boil-off of the liquid helium into gas, which expands explosively. Because of this, hospitals literally have to install specialized gas evacuation pipes and strictly monitor oxygen levels just to prevent thermal burns or suffocation if the quench actually happens.
Finally, Section 6, Electromagnetic Space Propulsion.
Okay, so if electromagnets can steer subatomic particles, peer inside the human body, and toss cars around like toys, could they push us completely out of our solar system? This brings us to a frankly mind-blowing concept from the U.S. Department of Energy. Program manager David Goodwin theorizes we could literally jolt a spacecraft through the deep cosmos without a single drop of traditional chemical rocket fuel. No propellants, just pure, unadulterated electromagnetic physics.
Goodwin noticed something incredibly interesting. When electromagnets are supercooled and electricity is first applied, they hit a non-steady state for just a few nanoseconds where they naturally vibrate. His engine idea basically capitalizes on this. He proposes using a supercooled niobium tin superconducting solenoid and rapidly switching it on and off. And when I say rapidly, I mean violently vibrating the magnet an astonishing 400,000 times per second. To actually sustain this in the deep freeze of space, the required setup is completely wild. Picture this, a continuous 300 kilowatt nuclear reactor running on highly enriched uranium. This reactor powers a giant solid-state switch, kind of like a massive computer chip, that constantly hurls 9,000 volts at 30 amps into a magnet cooled down to just 4 degrees Kelvin. And to turn all that stationary shaking into actual forward thrust, they introduce a metal plate, usually copper or aluminum, right into the magnetic field. This creates an asymmetry. Basically, it makes the magnetic force push harder in one direction than the other, resulting in a rapid, continuous forward jolt.
And this brilliantly illustrates the absolute limit-pushing potential of these devices. Now, Goodwin is the first to admit the engineering hurdles are massive, especially making sure the magnet doesn't literally vibrate itself to pieces. But if we can figure it out, this intense electromagnetic drive could propel a probe all the way out to the heliopause, the very edge of our solar system, roughly 200 astronomical units away. And it could get there traveling at a fraction of a percent of the speed of light.
So stepping back, it is just wild to think about. The exact same basic physics that started back in the 1820s, literally just a bare wire wrapped around a piece of iron on William Sturgeon's desk, hasn't just defined our modern electrical age, it might actually be the key to unlocking the deepest, darkest, most distant reaches of the cosmos. As we keep pushing the limits with advanced materials and supercoolants, you really have to wonder, what impossible boundaries will the electromagnets of tomorrow shatter next? Thanks for hanging out and exploring this with me today. Keep wondering, keep learning, and I'll catch you in the next explainer.